All right, so we're going to go over the first few pages of notes. Remember to break this up into several sessions instead of doing everything at once, especially at the last minute. It's a lot to take in, and you will absorb the information better, and it will stick with you more thoroughly if you split it up. At the top here, Michael Faraday on the left, James Clerk Maxwell on the right. Research each of them a little bit and write me a fun fact. I always like seeing the diversity of little fun facts that you guys can come up with. Below that, we've got Maxwell's equations, which I'm just briefly going to cover because we'll be going over these later on. The first one, Gauss's law, way back from the beginning of the semester, the closed surface area integral of the electric field dot product with the area element equals Q enclosed over epsilon naught, and this left-hand side is the net electric flux through that closed surface. The second of Maxwell's equations, again, a closed surface integral, area integral of the magnetic field will always equal zero. Just another way of saying that magnetic monopoles don't exist, and any magnetic field lines that enter a closed surface will exit. Magnetic field lines do not have a beginning or an end. They always form continuous loops, so impossible to have net flux through a closed surface. You can have magnetic flux through a open surface, but not a closed surface. Number 3 is Ampere's law, the closed loop integral. I know it's a line or a path integral because dA is area, dl would be a loop, a line, or a path. So dot product of B dl is mu naught I enclosed. This other term back here you haven't seen yet, that is Maxwell's addition to Ampere's law. And this says that not only will a magnetic field be created in space by a current that's enclosed in that loop, but if there is no current, you could have a changing electric field inside that loop and you would still get a magnetic field. So you don't need a current or moving charges to create a magnetic field. A changing electric field will also create a magnetic field. And that's a great insight by Maxwell. The fourth of Maxwell's equations is Faraday's law, which we will cover in this unit, the closed integral of the electric field, and this is dl, not dA, dl. So this is a closed loop integral similar to Ampere's law, is equal to the negative change in magnetic flux. We'll talk about what that negative means. That negative has to do with Lenz's law, which helps you figure out the direction of the electric field based on the changing magnetic field, or based on the changing magnetic flux. Basically, this electric field will oppose the change in the magnetic field, or the magnetic flux, sorry. Below this, we take a look at the main equations for this unit. This equation is just how you find magnetic flux, and we briefly covered that last unit as well. So phi B, magnetic flux, phi E, or maybe just phi would be electric flux. Same idea though, how much field lines poke through a given area. This is Faraday's law, and you'll notice it's a little different than the version of Faraday's law that I wrote up here. Epsilon here is a voltage, and voltage, remember, was the integral of E with distance, E dx. So this dl could be like a dx, so this is voltage, and this is the change in magnetic flux. So a change in magnetic flux you could use it to find the electric field that's created. You could also use it to find the voltage that's created, like in a loop of wire or something. Most of the time, you will use the left side of Faraday's law and the right side. It's not often that I have seen in the FRQ questions where you have to use this middle component. The last two equations here have to do with inductors. An inductor, kind of confusing, is just another name for a solenoid, but it's a special type of solenoid. It's a solenoid that's in a circuit. And we'll look at those in another set of notes after we go through these few pages here. That'll be next week when we look at that. On the next page, Faraday's law. Magnetic flux itself does not create an electric field, but when that magnetic flux changes, it will create an electric field. The electric field goes around a distance, which creates a voltage, and if there was a wire there, it would create a current in it. Faraday's law relates the change in magnetic flux through a surface to the electric field that's created around the edge of the surface. And anytime you have a changing magnetic flux, it will create an electric field. Then if there is something in space which can react to that electric field, like a moving charge or a charge that's free to move, like electrons in a wire, they will move and that would create a current. But it's important to note that this law is true regardless of whether something is actually in space. Anytime you have a changing magnetic flux, it will create an electric field. Whether or not something that is there to interact with the electric field, it gets created. So this is an induced voltage. We already discussed that. Closed loop integral. This is a line or a path integral. Time rate of change of the magnetic flux. And if you combine the equation here for magnetic flux, that will be the time rate of change of this dot product. And of course, EDL dot product, EDL cosine theta. And this would be BDA cosine theta, but this theta and that theta might not be the same. So Lenz's law is kind of a conceptual way of understanding the negative sign in Faraday's law. When an induced current gets created from a changing magnetic flux, it will be created in such a way that the new magnetic field created by the induced current, remember, a current moving around in a loop of wire will create a magnetic field. There's a right-hand rule for that. This current that gets created will want to fight or prevent the change in magnetic flux. So there's going to be another version of the right-hand rule here. Keep these things all straight. To use Lenz's law, you're going to determine which direction the change in flux is pointed. Here's a way to do that. If the magnetic field is increasing, the change in flux is in the same direction as the magnetic field. However, if the magnetic field is decreasing, the change in flux is opposite the direction of the magnetic field, okay? Opposite the direction of B. So increasing, same direction as the magnetic field. If the field decreases, the change in flux points the opposite direction of the field. Once you know which direction the change in flux is, we know that the current that's going to be created wants to fight or prevent that change. So you're going to point your right-hand thumb in the opposite direction of the direction that the flux was changing. And then you curl your fingers, and that's the direction of the induced current, or the direction that the electric field would be. So here the electric field increases, right? And we already said here that if the electric field or the magnetic field increases, the change in flux is in the same direction. So the change in flux is upwards because the magnetic field points upwards and it's getting bigger. So you're going to point your thumb down, which is the opposite direction as the change in flux. When you curl your fingers there, your fingers will curl in a clockwise fashion if you were viewing this from above. So once you know that, go to the diagram and draw. So the current here would be that direction. Over here it would be that way, that way, that way, that way. So that's the induced current. The opposite is true if the magnetic field is decreasing. When the magnetic field decreases, the change in flux is in the opposite direction of the magnetic field. So in this case, the field points up, but its strength is growing smaller. So you point your thumb down. The change in flux is down. You point your thumb up and then curl your fingers. Okay? Field decreases, change in flux is the opposite direction of that. So change in flux is downwards. You point your thumb in the opposite direction as the change in flux. So point your thumb up, curl your fingers, and you'll find that the current then goes in the opposite direction here. So there's the induced current. The very bottom of this page just kind of sums up what we just went over. Changing magnetic flux through a wire loop creates a voltage and a current in the wire loop such that the magnetic field created by the current opposes the change in the original magnetic field. So if you remember the right-hand rule, if we have a current going, this would be clockwise from above, to find the direction of the magnetic field that this current would create, you curl your fingers in the direction of current and your thumb will point down. And notice that when your thumb points down, it opposes the growing magnetic field upwards. That's the idea. It's always going to create a current such that this current creates another magnetic field which opposes the change in the original one. Now, even if a loop of wire is not here, you will still have an electric field created in space, and that electric field will be circular around the loop. All right, so that's going to be it for now. We'll pick up with another video in the next one.